Yes, it's a dot, which is where it gets its name, dot product. Now that also looks like what other math symbol? So how you're going to know it's not multiplication is that it doesn't make sense to multiply vectors. There's no application where you ever need to multiply vectors. So this dot, I think it's supposed to be slightly bold, but it's never going to be multiplication. Okay, so the more formal definition to dot product would be like you had vector P, and it was P1, P2, and Q, which is Q1, Q2. To compute the dot product, you would want to take P1 times Q1 and P2 times Q2, and then you add those values together. It's a little wordier than it actually is. Basically just saying take the horizontal components together, multiply them together, take the vertical components, multiply those together, and then you add them up in the end. So for those, it would be 8 plus 15, so 23. Dot product should just give you a number, or it's scalar. Scalar is a fancy word for a real number. Okay. Again, so if you want dot product of two vectors, not multiplying. I'm multiplying this part of this with this part of that, and then multiplying this with this, but you don't just straight multiply. Okay, so if I multiplied the horizontal components here, that would be 3. If I multiplied the vertical components, that would be negative 70. And dot product, you just add them up. And you end up with a number. Sure. Alright, so we're going to look at 3 different ways to use dot product. 2 of them are definitely necessary. One is just kind of an option. Just something that we did in 6.3 if you want to look at that. Okay, so first use of dot product. If 2 vectors have a dot product of 0, so if we do this work and we get 0, then they are going to be perpendicular, which means they intersect at a right angle. But for vectors, we don't really say perpendicular. It's got a fancier word like orthogonal. So when you're asked if something is orthogonal, it's asking, is the angle between those 90 degrees? So I guess you could sketch them and you could look at it and you could get a good idea if there was a right angle between them. But short of just guessing based on what your picture looks like, you want to use dot product. Multiply the horizontal components together, multiply the vertical components together, and when you add that, if it gives you 0, then they will be orthogonal. Dot product is 0, so there would be a right angle between them. But if you found the dot product, multiply the horizontal components, multiply the vertical components, add them up. If the dot product is not 0, then no, they are not orthogonal. The dot product is not 0. So something else, some other angle besides the right angle. Okay, so there's one use of dot product. Very easy to just give a yes or no, not being orthogonal. Okay, so another use, second use for dot product, and this is just an alternative, so you might prefer this to what we did in section 6.3. So I want you to compare what we did in 6.3 with another way to do that. So in 6.3, I wanted you to find the magnitude of this vector. You probably should have sketched it. Right 3, down 4, and from the sketch, you had a right triangle, and Sometimes you need Pythagorean theorem, although that one's like Pythagorean triple. And okay, so let's say this wasn't a Pythagorean triple. We would need to pull out Pythagorean theorem. I do want you to write these steps down this time, even though I know you understand why the magnitude is 5. We plug in a leg and square it, plug in the other leg and square it. We get 9 plus 16 is c squared. 25 is c squared. The hypotenuse is the square root of 25. So the magnitude ends up being 5. Again, that's the way we approach it in section 6.3. And there's nothing wrong with that. That's fine. If you don't mind sketching the picture, skin the right triangle, plug in the numbers in the Pythagorean theorem correctly, then you get an answer of 5. But as an alternative, so now that we're in section 6.4, you can also take the dot product of a vector with itself. So the vector 3, negative 4 with itself, 3, negative 4. You could find its dot product. So you would multiply the horizontal components together to get 9. Multiply the vertical components to get 16. You would add those together, and the dot product would be 25. And then step 2 says take the square root of that. Same thing you get doing the other way. In some ways, this is easier because I wrote down less stuff than I had to write down over here, but I guess it kind of depends on the number. Okay, so one more example to help you see achieving the same thing, just a different approach. I want to find the magnitude of negative 2, 5. I could sketch left 2, up 5, Pythagorean theorem. I know the legs. We get 25 plus 4 is c squared, which is 29. And in the end, I take the square root of 29. So its magnitude is the square root of 29. Or, to get the same information, I could take the vector negative 2, 5, and start off by taking the dot product of that vector with itself. So I would multiply the horizontal components together to get 4. Multiply the vertical components together to get 25. Dot product says to add those together, which would be 29. And if you're going to do that, just make sure you don't also forget to take the square root of the end. Square root of 29, square root of 29. Same magnitude both ways. The reason why I like you to write it both out is you can see whether you take the square root at the end here or you take the square root of the root here, it's the same. Negative 2 squared ends up being 4. Negative 2 times negative 2 ends up being 4. 5 squared ends up being 25. 5 times 5 ends up being 25. The work is very, very similar. You okay with that connection? And lastly, the third use for dot product is to find the angle between two vectors. You do have to know this formula. I don't think we're going to give that to you on a formula sheet. For sure you need to memorize that one. So sometimes we want to look at it like this, and if we're trying to find the angle, of course we would do inverse cosine of that. And so that would be inverse cosine of u dot v, so that's dot product, divided by the magnitude of u times the magnitude of v. No matter what the angle is in between the vectors. So like, remember there was one homework question in the last session where they asked you to do something like that. And it was kind of a pain in a roundabout way to find the answer, and I did not worry about it because you didn't need to worry about it for that quiz. But also because we just have a formula that handles that for us. Okay, so I'm going to do two of these, and I want you to actually practice one of these. I want to find the angle in between these two vectors. Let me sketch what this would look like. Right 4, up 3. I'm going to try to draw this scale the best I can too. And this one is right 3,
of 5. So this formula will tell me this angle right here. The angle tracked between those two vectors. Okay, so if I want the angle, it'll be inverse cosine of the dot product of the two vectors divided by the magnitude of the two vectors multiplied together. So of course, you've got to be able to compute the dot product. Multiply the horizontal components together, you get 12. Multiply the vertical components together, you get 15. And dot product, you add those two values together. So there's 27. Okay, I've got a sketch here, so I'm not going to re-sketch this. This is U. So it's a 3, 4, 5 triangle. Hypotenuse is 5. And V, this was 3, this was 5. So therefore its magnitude must be 4. It's a 3, 4, 5 triangle. You okay with that? You shouldn't be. This is 3, this is 5, this is 4. It's only a 3, 4, 5 triangle if it besides the hypotenuse. So this one you have to do Pythagorean theorem or this stuff if you'd rather. It is the square root of 34. Even if the square root of 34 reduces, don't bother. And you've got a square root in the denominator, don't even bother rationalizing either, because this is ready to go into our calculator. Ready to throw that in there, and assuming we're in degree mode, because that's what we're looking for here. And we type it in carefully. .166 degrees. So if you have a good sketch, you have an idea if that seems realistic or not. 22 degrees seems to make sense with my picture there. I could believe that. Okay, let me do one more of those. And again, I'm going to try to do a picture, but this one's not great either. So another 3, 4. So this one would have the magnitude of 5. 3, 4, 5 triangles okay as long as the hypotenuse is the 5. And then 6, 10, this. So this morning, 0 hour, when I did this one, I hit one wrong button in my calculator. I got an answer of like 77 degrees or something. There's no way this is 77 degrees. This is a terrible sketch, but I can tell 77 is way too much. It should be pretty small here. I don't know, I could maybe buy 20 something, but it's even smaller than that. So you can know the formula. Either this or this. Sometimes it's better to start with that. Plug in the dot product. So the dot product would be 18 plus 40. That's the horizontal components multiplied together plus the vertical components multiplied together. With a little bit of practice, you don't even need to write it down usually. Divided by the magnitude of this vector, which right now is 5. It's a 3, 4, 5 triangle, times the magnitude of this right triangle, which would be leg squared plus leg squared equals hypotenuse squared, so the square root of 136. And square root of 136 may break down, and that's not rationalized, but it doesn't matter to us right now. So we're going to let our calculator evaluate all that stuff in here. almost 6 degrees. So a very small difference. The better you draw your picture, the more to scale your picture is, the more confidence you have in it. Should be very, very small difference. Okay, so I'd like you to practice that one time. And then probably once or twice in the homework. But go ahead and try number 9 and see if you can catch all the stuff that you're supposed to catch. So maybe sketching a picture wouldn't be a bad idea, but I guess it's also not necessary to try to find that angle. So if you started off here, the horizontal components give you 12, the vertical components multiply to negative 12, so what's to make the dot product? Okay. You find the right 2 down 3, you go and find its magnitude, and that would be square root of 13. Find this magnitude, right 6 up 4, should be 36 plus 16 is 42, square root of 42, is that right? 52? Okay, doesn't matter that these are messy. You go and type all this in your calculator, and then hopefully you realize that you did more work, or obviously I hope that you caught that, but I hope that you saw that you may have done too much work. Because look at what you're asking your calculator. 0 divided by anything is going to be 0, right? So you're really asking your calculator, what angle has a cosine of 0? And what angle has a cosine of 0? 90, which you could have caught from the very beginning if you saw that the dot product was 0. That was the first use of dot product. The dot product is 0, it will be orthogonal. You'll have to write it between. But if you don't catch that, it's not a big deal because it'll still work out just fine for you. Okay. And then finally, we like to look at what you need to know that scalar is just kind of a fancy term that means a real number. So a few of the questions in the book assignment, a few questions on the quiz, we'll ask you to do like dot product and then state whether it's a scalar or a vector. So if you just do dot product, you're going to have a number like 1 or 0 or what else we get, 27. Those are scalars. So they want you to say that it's a scalar. And then some of them want you to take that and then multiply it by a vector, and then say your answer would be a vector. So you need to know what's not associated. Okay. And finally, we like to mix in 2 kind of application problems, which end up being super easy because there's no real variation to these. It will always be just like this. And so one of them that we look at is a simple work formula that says work So work is like how much energy is required to move something or to do something. And the formula that we're going to use is work is equal to force times distance times cosine of theta. So this capital F is force. So moving a 1 pound object is going to be a lot easier than multiplying a 100-pound object. This D is for distance. Moving something 1 foot is a lot easier than moving it 100 miles. So that takes care of that. And then the angle that we plug in is going to represent the efficiency. Because cosine deals with horizontal distances. So if you're trying to move something, pushing your work at a 10-degree angle is different than pushing it at an 80-degree angle. Both of those would move the object, but one of them is going to be more efficient than the others. Okay, so the classic example here is someone mowing a lawn. So the angle that it's talking about, the angle makes a 40-degree angle with the ground. That's like from here, this is 40 degrees. Okay, I want to move it 100 feet, that's distance. And if the mower weighs 55 pounds, that's how much force you have to exert. So the work being done is going to be force times distance times cosine of theta. So in this question, 55 pounds, 100 feet at a 40-degree angle. So as this angle increases or decreases, it makes a difference in how much work we have to put into this. So that's my calculator. What's 55 times 100 times the cosine of 40, and that is 4,213.244. And I put the units here so that you can see we've got pounds, we've got feet, and so these are referred to as foot pounds. Now, if you're in physics or you're going to take physics, I think you normally work in like joules. Joules, so the difference, there's not much difference, but the difference between foot-pounds and joules have to be in newtons, you can have seconds, you can have meters, and you can have kilograms. So you wouldn't use pounds. Like if you want to convert this pounds to kilograms, and you want to convert these feet to meters, then you could say it in joules. But let's say that it's in pounds. So just like with the unit circle, cosine deals with the horizontal change. So like if you think about this like as a big right triangle, if you're trying to push this, you care how much is being pushed horizontal. So that's why it's cosine and not sine. You could, but no one really cares. Like, if you're mowing the lawn, no one's asking you, like, how much of your energy went into pushing the mower into the ground. Yeah. But you probably do, like, other variations of this formula, right? Yeah. We'll only make you use this one. That's why it's super easy. Okay, so notice I made one change here. Still the same mower, 55 pounds. I still want to move it 100 feet. So what if I adjust the angle, this angle, to 80 degrees? Now it's going to take a whole lot less work. That angle makes more sense. as far as being efficient with your energy. Yeah, so you could do that if you wanted to, but this is what we're going to ask you to do. So it's one formula, and we got to give you the three things, so you basically just got to know that. That's easy. And then finally, the last type of problem we're going to do is look at how much force is needed to keep an object from rolling downhill. And so there's really only two things that can change about these questions. I mean, you can change what object you're talking about, so it really does not matter. How about an elephant? How much do you think an elephant weighs?
6 tons.
Okay, I think I heard 600 pounds first. About 13,600. Okay, it doesn't matter. If you don't like the estimate, change what the object is. Okay, and then the other thing that can change is how steep the hill is. So let's say that a normal hill that you would want to be walking around on, probably going to be not all that steep, maybe 5 degrees. Okay, so the work here, the majority of the question is going to be setting up this picture. Guys, I need y'all to refocus here. So each of these questions, you're going to have, here's your hill, here's the ground. Somewhere on this hill is your object. And when you say that something weighs 13,600 pounds, just like if you stand on a scale, you don't stand on it like diagonally. Your weight is how much you're pushing towards the ground perpendicular. So this would be the 13,600. Okay, to complete your picture, you need to understand that your weight, or this elephant's weight, standing on a hill, some of their weight is pushing into the hill, which we call force perpendicular. And there are some rare instances where you care what that was. Maybe this hill is actually like a piece of glass, and you need to know how much weight's being pushed in for it to know if it's going to crack. And then there's this, which is the force downhill. So some of the weight is pushing into the hill, and some of the weight is pushing it down the hill. Well, if you can figure out how much force is being pushed down the hill, that's the same as how much force you need to exert to keep it from rolling downhill. Obviously in the opposite direction. But we ultimately want to figure out what's the magnitude of that vector. How much of its weight is pushing it down the hill, so we know how much we have to push back to keep it from it. Now, luckily, this force is equal in magnitude to this vector, which most people call the force parallel. And I call it the force parallel because it's parallel to this one. And these will have the same magnitude. And because these are parallel, and this is perpendicular to this one, from the transitive property, this one would have to be perpendicular to that one. And this particular example is at 5 degrees. So you don't normally need to do this much angle chasing, but you should be able to. If this is 5 and this is 90, this one in here would need to be 85. And if this is 90 and this is 85, this one here is. So this angle and this angle will always be the same. But again, you can find that on the spot. Okay, so there's the setup. That's the part you have to understand how to sketch. But then in the end, what I'm really focused on is this right triangle. And this length, or force, I know this angle, and it's a right triangle. So I'm just trying to pull this over to the side. That's what I'm focused on. If I want to know the force perpendicular, I could use a cosine equation. Cosine of that angle, I could pair up adjacent over hypotenuse. So 13,600 times the cosine of 5 tells me that 13,548 pounds is pushing into the hill. Which should make sense because the hill's not very steep. Most of the weight is pushing into the ground. If I want to figure out this, the force parallel, because it is equal to the force downhill, which is equal to the force that I would have to keep it from falling downhill, I would be trying to find the opposite side of the right triangle when I know the hypotenuse. So sine is opposite over hypotenuse. So the amount of force I would need to keep if I'm rolling down the hill would not be too much, because most of it's going into the hill. But probably still more than I could use with just my body. So, assuming the elephant's not helping you, they're just standing there, and the only force that's acting upon is gravity. This is how much we'd have to push back, because that's how much it's pushing down. Okay, so now let's look at maybe more extreme numbers. Let's pick a weight that maybe a person can do. You weigh 210? 150. Okay, so we're just going to practice setting it up again, but in the end, you're just finding two sides of the right triangle. Just knowing how to set it up. What are you going to get? Okay, let's pick a much steeper hill this time. 15? How about one now? Here's a much nicer. Usually classes want to do like a 90 degree or an 89 degree, which would be a cliff. So if it was 90 degrees, we're going to do 90 right now without writing it down. If it's 90 degrees, how much force would you have to exert to keep them still? All of it. 150. If you want to keep them in place and they weigh 150, you would have to push back 150. To keep them in the same spot, keep them from falling down. All of it would be. And you could do that. It's just that the cosine of 90 would be 1, so you'd be multiplying the weight times 1. Okay, let's go with 30 though. So we've got a hill. Person weighs 150 pounds, which is perpendicular to the ground, not perpendicular to the hill. Some of that weight is perpendicular to the hill, and some of that weight is pushing it down the hill. So force parallel, or force downhill, and force perpendicular. By the way, you don't need to add up to 150 either. You shouldn't add up to 150. The force downhill is equal to the force parallel, so we should probably draw this in as well. And that ends up giving us the right triangle, where we would like the two other sides and we know one side. So I need to know at least one of these angles. So if we pick 30 degrees, and then this is 90, then this would be 60, And if this is 60 and this 90, this would need to be 30. Although those two will always be the same. And then force perpendicular. Okay, so this one is a glass, this one's on the hill. I would want a cosine equation, because the cosine lets me put the adjacent side over the hypotenuse. So the amount of weight pushing into the glass would be 129 pounds. And the force parallel, which is equal to the force downhill, which is how much force I would have to require to keep it from going down. I would be interested in knowing the opposite side when I know the hypotenuse. So that would be a sine equation. And that comes out to be exactly 75 pounds. So assuming no other forces, only gravity, I'm probably not going to be able to push back almost 100 pounds and keep it long downhill, even if it's on a very steep hill. If you weigh 150 pounds and we're on a steeper hill, you're still only pushing down the hill at 75 pounds, so I could probably push back and keep you from going down. This you could do with a machine, this is probably right. But it all comes down to just finding two sides of the right triangle. You just need to make sure that you practice setting it up so that you can do instead of equations. Okay. Well, it depends on how hard. If you want to push it uphill, then any more force than that would push it uphill. It depends how far you want to go uphill and how fast you want to go uphill. But if you just want to go uphill, push 76 pounds or 75.1 pounds. You would be going much uphill, but it would be some. Okay. So you got just a few minutes before your lunch break, so I'm not going to ask that you start with this assignment, but I think you should probably go ahead and copy the assignment down to the top of your page. There's only 13 questions. It definitely should be achievable in this class. We do need to make a small change for the next class to what the assignment sheet says. The assignment sheet says that I've been giving you the practice quizzes today. So I'm going to actually give that out in the next class. And what I hope to do is to give you that, and work with that, and ask questions the first half of the class, and then do the second half of the class. But that's not going to be an option because so that day I will only see you guys for like 30 minutes and a half. It's not going to be time to do that. So I'll give you the practice question as soon as time. But the quiz will be the class after that. But today you should get all the practices we need.